Welcome to this module, Core Cryptographic Primitives. In the previous module, we learned why PKI exists. Now we're going to understand how it actually works. Think of cryptographic primitives like Lego blocks. A single Lego block isn't very useful by itself, but when you combine many blocks, you can build a house, a castle, or a spaceship. Cryptographic primitives work the same way. Each primitive solves one specific narrow problem. It's designed to be secure, well-tested, and reusable. When you combine multiple primitives together, you create complex systems like PKI. In this module, we'll explore 4 core primitives: hash functions, digital signatures, key pairs, entropy, and randomness. These 4 building blocks are the foundation of everything in PKI. If you understand these, you understand the mathematics underlying certificate authorities, trust chains, and modern security. Let's start with hash functions. A hash function is a mathematical function that takes any input. It could be small, it could be huge, and produces a fixed size output called a hash. Think of a hash like a fingerprint. Everyone has a unique fingerprint. Even identical twins have different fingerprints. You can look at a fingerprint and identify someone, but you can't reconstruct the person from their fingerprint. It's a one-way transformation. A cryptographic hash function has 5 critical properties. First, deterministic. This means the same input always produces the same output. If I hash the word hello today, I get the same hash as yesterday as next year. It's predictable, but only if you know the input. Second, fast. Hashing is computationally efficient. Modern computers can hash gigabytes of data in seconds. Third, avalanche effect. This is crucial for security. If you change the input by even one tiny bit, one letter in a message, one bit in binary, the entire output hash completely changes. In a good hash function, changing one bit should flip approximately 50% of the output bits. This makes it impossible to modify a document without completely changing its hash. Fourth, non-reversible. You cannot reverse a hash. Given a hash output, there is no mathematical way to figure out what the input was. This is why it's one way. Fifth, collision resistant. A collision is when 2 different inputs produce the same hash. This should be extremely rare, so rare that it's effectively impossible with current computing power. A good hash function should have no known collisions. These properties combine to make a hash function perfect for creating unique fingerprints of data. Let's look at some real hash functions you'll encounter in PKI. The most common family is SHA-2, which stands for Secure Hash Algorithm 2. There are 2 popular variants: SHA-256, which produces a 256-bit output, 64 hexadecimal characters; SHA-512, which produces a 512-bit output, 128 hexadecimal characters. SHA-2 has been the industry standard for years. It's used in Bitcoin. Every single Bitcoin transaction relies on SHA-256. It's used in SSL/TLS. Every HTTPS connection on the internet likely uses SHA-256. It's used by governments and militaries worldwide. Then there's SHA-3, also known as PKI. SHA-3 is a newer algorithm that takes a completely different mathematical approach than SHA-2. It's more resistant to certain types of future attacks. As systems upgrade, they're moving from SHA-2 to SHA-3, but SHA-2 will remain standard for years. There's also Blake-2, which is even faster than SHA-3 while maintaining cryptographic security. It's becoming popular in modern systems. Now, you should know about some legacy algorithms. MD5 and SHA-1 are older hash functions. MD5 has been broken, meaning collisions have been found. SHA-1 has been weakened. I strongly recommend you avoid these for any new systems. If you're still using them, make it a priority to upgrade. Let me show you a concrete example. If I take the phrase hello world and hash it with SHA-256, I get this 64-character hash. Now, if I change just one letter, lowercase w instead of uppercase W, I get a different hash. These 2 hashes are completely different. Even though the inputs differ by one letter, the outputs share no common pattern. This is the avalanche effect: tiny input change, massive output change. Now let's see how hash functions are used throughout PKI. First, certificate fingerprints. Every certificate has a hash. This hash serves as a unique identifier. If you want to verify that a certificate is legitimate, you can compare fingerprints. For example, a website might publish their certificate fingerprint on their website. Our certificate SHA-256 fingerprint is A422CB0. Then when you connect, your browser can verify this matches. If someone tries to use a fake certificate, the fingerprint will be completely different. Second, digital signatures. We'll explore this in depth in the next slide, but the key point is that before you sign something, you hash it first. This makes signing much faster and more practical. Instead of signing a multi-gigabyte video file, You sign a tiny hash of that file. Third, certificate revocation lists. When a certificate needs to be canceled, maybe the private key was stolen, maybe the owner left the company, it's added to a revocation list. Hashes identify which certificates are revoked. Fourth, integrity verification. If even one bit of a certificate is tampered with, the hash changes completely. This allows the system to detect any modification. The certificate might have been intercepted and altered. The hash will reveal it immediately. Fifth, key derivation. You can derive multiple encryption keys from a single master key using hashing. Or you can hash a password to create an encryption key. Hashing provides a secure way to transform data into keys. These applications show how fundamental and versatile hash functions are in PKI. They're used everywhere. Now we come to digital signatures, one of the most powerful concepts in cryptography. The problem we're trying to solve is this. How do you prove that you created something? How do you prevent someone from modifying it after you created it? How do you prove who signed it? In the physical world, you sign documents with a pen. But handwritten signatures are easy to forge. Anyone with a pen can imitate your signature. Digital signatures solve this because they're mathematically unique to you. Here's how it works, step by step. Step 1. You have a message you want to sign. Step 2. You hash the message. This creates a unique fingerprint of the message. Step 3. You encrypt this hash using your private key. This encrypted hash is your digital signature. It's unique because only your private key could have created it. Step 4. You send both the message and the signature to the recipient. Now the recipient verifies the signature. Step 1. They receive the message and the signature. Step 2. They hash the message using the same hash function you used. Step 3. They decrypt the signature using your public key. Remember, if you encrypted with private key, you decrypt with public key. Step 4. They compare the hash they just computed with the decrypted signature hash. Step 5. If these hashes match exactly, the signature is valid. The message is authentic. You really did sign it, and it hasn't been modified. This is incredibly powerful. It proves you created the message, authentication. The message hasn't been modified, integrity. You can't deny you signed it, non-repudiation. The recipient didn't need any secret information from you. They only used your public key, which is, well, public. Anyone can verify your signatures. You might be wondering, why sign the hash of the document instead of the whole document? The answer is efficiency. Hashing is incredibly fast, milliseconds, even for massive files. But signing is computationally expensive. It requires complex mathematical operations. Signing a 1 GB video file directly would take hours of computation. But hashing that gigabyte file takes maybe 1 second. Then signing the 256-bit hash takes maybe 10 seconds. The difference is dramatic. You're signing a tiny fingerprint instead of the whole document. But there's another benefit, security. When you sign a document, you're essentially encrypting it with your private key. Encryption is computationally expensive, and it has limitations on message size with some algorithms. By hashing first, you reduce the data to a fixed small size that's easy to sign. Also, signing directly would leak information about the document through the signature. By hashing first, and hashing is one-way and non-reversible, you protect the original content of the document. So hashing first gives us both efficiency and security. Digital signatures are woven throughout every part of PKI. Let me show you where. First, certificates themselves are signed. When you request a certificate from a certificate authority, the CA takes your certificate data, hashes it, and signs it with the CA's private key. This signature proves that the CA created and approved your certificate. Anyone can verify this signature using the CA's public key, and if the signature is valid, they know the CA really did issue this certificate. Second, certificate revocation lists are signed. When certificates are cancelled, they're placed on a revocation list. This list is signed by the CA. It can't be forged. Third, signed communications use digital signatures. If you want to send a confidential email that's also digitally signed, you use S-MIME Secure MIME. You sign the email with your private key. The recipient can verify using your public key that you really sent this email. Fourth, code signing. When a software company releases new code, they can sign it. Users can verify that the code really came from that company, not a counterfeit. This is critical for preventing malware. Fifth, challenge response authentication. A system can challenge you by asking you to sign a random value. If you can produce a valid signature with your private key, you've proved that you possess the private key, which proves your identity. And because the random value changes each time, the authentication can't be replayed. Every single one of these applications is critical to security. Without digital signatures, PKI would not work. Now, let's talk about key pairs, the core of asymmetric cryptography. A key pair consists of two mathematically related keys. A public key, which can be shared widely. You can publish your public key everywhere, email, websites, directories, and it doesn't matter if it leaks. A private key, which must be kept secret. This is like your password, except even more important. If your private key is stolen, your entire security is compromised. The mathematical relationship between these keys is the magic of asymmetric cryptography. If I encrypt something with your public key, only your private key can decrypt it. If I sign something with my private key, your public key can verify my signature. But here's the really interesting part. Even though these two keys are mathematically related, the private key cannot be easily derived from the public key. Theoretically, it's impossible. Practically, deriving the private key would take so long with current technology that it's unbreakable. Now, key sizes vary depending on the algorithm. RSA keys are typically 2048 or 4096 bits. That's 256 or 512 bytes. Elliptic curve keys are smaller, 256 or 384 bits, but provide equivalent security. Why the difference? It's about the underlying mathematics. RSA is based on the difficulty of factoring very large numbers. To maintain security against increasingly powerful computers, RSA keys must get bigger. But ECC elliptic curve cryptography is based on a different mathematical problem that remains hard even with smaller key sizes. The key size determines the security level. A 256-bit RSA key would be breakable in seconds. A 256-bit ECC key provides strong security against any attacker with current technology. How do you actually generate a key pair? The process might seem simple, but it's critical that every step is done correctly. The key is only as secure as the randomness used to generate it. The process starts with entropy collection. Entropy is randomness. Your operating system gathers random data from many sources: the timing of disk access, mouse movements, network packet arrival times, thermal noise, and other sources. Hardware security modules might also have special hardware random number generators that use quantum effects or atmospheric noise. All these entropy sources are mixed together in an entropy pool. This gives you high-quality, unpredictable randomness. Then you use this entropy as a seed for key generation. The cryptographic library, like OpenSSL, takes the entropy, applies mathematical functions, and generates the prime numbers needed for RSA or the curve points needed for ECC. Finally, the library validates the generated keys. It checks that the mathematical properties are correct, that the keys meet security requirements, and that there are no weaknesses. To generate an RSA key, you might use OpenSSL JSON 4096. To generate an elliptic curve key, OpenSSL's ECPRM name, prime 256 votes Genki. For sensitive keys used in certificate authorities or critical systems, you'd use a hardware security module, an HSM. The HSM generates the keys internally and never exports the private key unencrypted. This ensures the key is protected even if the computer is compromised. There are two main algorithms for asymmetric cryptography: RSA and ECC, elliptic curve cryptography. Let's compare them. RSA stands for Rivest, Shamir, and Adleman, the three mathematicians who invented it. RSA is based on the difficulty of factoring very large numbers. Here's the basic idea. Multiplying two large prime numbers together is easy. A computer can do it in milliseconds. But if you give someone only the result and ask them to figure out which two primes were multiplied, it becomes extremely hard. This asymmetry, easy one way, hard the other way, is what makes RSA work. RSA has been around since 1977. It's well understood, extensively studied, and has been proven secure through decades of scrutiny. This is its biggest advantage. It's battle-tested and trusted by everyone. But RSA has disadvantages. To maintain security as computers get faster, RSA keys must get bigger and bigger. A 2048-bit RSA key is standard today, but some organizations are moving to 4096-bit for long-term security. Bigger keys mean slower operations, more computation, and more power consumption. Now consider ECC elliptic curve cryptography. This is based on a different mathematical problem, the discrete logarithm problem on elliptic curves. The mathematics is more complex, but the result is that you get strong security with much smaller keys. A 256-bit ECC key provides security equivalent to about a 3072-bit RSA key. The operations are also faster because the numbers are smaller. This makes ECC perfect for IoT devices, mobile phones, and any system where computation power or battery life is limited. ECC is newer than RSA. It was invented in the 1980s but took longer to be widely adopted. But the trend is clear. New systems are using ECC. It's the future of cryptography. For your organization, if you're choosing algorithms for new systems, ECC is the recommended path. For legacy systems still using RSA, 2048-bit minimum, 4096-bit preferred. Here's a question that keeps cryptographers awake at night. How do you generate true randomness? Entropy is randomness, it's unpredictability. In cryptography, entropy is critical. If an attacker can predict your random values, your security is broken. They can predict your keys, predict your nonces, predict your challenges. Everything crumbles. There are two types of randomness. First, true random number generation, TRNG. This uses physical phenomena that are genuinely random. For example, you could measure atmospheric noise, electromagnetic interference in the air. You could measure radioactive decay. You could use quantum effects like the behavior of electrons. These are truly unpredictable. They're perfect for generating cryptographic keys, but they're slow. Generating enough entropy from physical sources to create a 2048-bit RSA key can take minutes or hours. Second, pseudo-random number generation, PRNG. This is a deterministic algorithm that produces sequences that appear random, but are actually determined by a seed value. If you give it the same seed, it produces the same sequence. PRNGs are fast. They can generate millions of random values per second. The trick with a PRNG is that the seed must be unpredictable. If you seed a PRNG with true entropy, you get the best of both worlds. True randomness from the entropy, combined with speed from the PRNG. Modern operating systems maintain an entropy pool. On Linux and Unix, this is accessed through dev urandom. On Windows, it's cryptgenrandom. The OS collects entropy from multiple sources and mixes them together. When you need random values, you request them from this pool. Now, here's where things can go very wrong. If your entropy sources are weak or predictable, your entire security fails. I want to tell you about two real incidents. In 2006, a team of researchers discovered that many embedded systems were generating weak keys. Why? Because they didn't have good entropy sources. They were seeding their PRNGs with the current time or device ID values that might be predictable. Thousands of devices had weak keys that could be broken. In 2008, the Debian Linux project accidentally weakened the entropy pool by removing code that gathered entropy. For months, all keys generated on Debian systems had reduced entropy. When this was discovered, it was a massive vulnerability. Every key generated in that period had to be regenerated. These incidents show how critical entropy is. It's not something to take for granted. Where does entropy matter in PKI? First, key generation. When you generate a certificate key pair, you need high-quality entropy. The key must be unpredictable. If an attacker can guess your private key, they can forge your signature or decrypt your secrets. Second, TLS sessions. Every time you establish an HTTPS connection, new session keys are generated using TLS's key agreement protocol. This requires entropy. Modern TLS uses perfect forward secrecy, which means every single session gets new keys. With billions of TLS connections happening every day, you need a constant, reliable source of entropy. Third, nonce generation. A nonce is a one-time value. It should never be reused. Nonces are used in digital signatures, in authentication challenges, in cryptographic protocols. Each nonce must be unpredictable and unique. In a hardware security module, an HSM entropy is carefully managed. HSMs often have hardware random number generators built in. They use dedicated processors to ensure entropy is high quality and abundant. This is why HSMs are preferred for generating critical keys. For your organization, you should understand how your systems generate randomness, what entropy sources are available, whether entropy is sufficient for your scale, how to monitor entropy health. If you're generating thousands of keys or millions of TLS sessions, you need abundant entropy. Running out of entropy is a real problem that can cause services to slow down or fail. A good practice is to use a hardware security module for critical key generation. HSMs are designed specifically to generate high-quality, unpredictable keys, even at massive scale. Now, let's see how all four primitives combine to create PKI. Imagine you want to get a certificate from a certificate authority. Here's the complete process. First, the CA generates its own key pair. This requires high-quality entropy. The key is generated cryptographically secure and is stored in an HSM-protected hardware. The KeyA's public key is published widely so anyone can verify certificates. Second, you decide you need a certificate. You generate your own key pair using secure randomness. You keep your private key secret. Third, you submit a certificate signing request, a CSR, to the CA. This request contains your public key and information about you. Fourth, the CA verifies your identity. They check documents, verify your ownership of domain names, whatever is appropriate. Fifth, the CA creates a certificate document. This document contains your name, your public key, when it expires, and other information. Sixth, the CA hashes the certificate. This creates a unique fingerprint. Seventh, the CA signs the hash using its private key. This signature proves the CA created and approved the certificate. The signature is attached to the certificate. Eighth, the certificate is published. Anyone can now look it up. When someone wants to verify your certificate, they download your certificate and the CA's public key, which they already trust. They hash your certificate to get a fingerprint. They decrypt the signature using the CA's public key. They compare the two fingerprints. If they match, the signature is valid. They trust your public key because they trust the CA, and the CA endorsed your key with their signature. This is the complete PKI system. Entropy enabling secure key generation, keys enabling asymmetric cryptography, hashing enabling efficiency, signatures enabling trust. All four primitives working together. Now that you understand the primitives, let's talk about what can go wrong. Weakness in hash functions. If a hash function has collisions, two different inputs producing the same hash, an attacker could create a fake certificate with the same hash as a legitimate one. This happened with MD5. Attackers could forge certificates. The solution: use SHA-2 or SHA-3. Never use MD5 or SHA-1 for new systems. Weak key generation. If keys are generated without enough entropy, an attacker might guess the private key. This happened with some embedded systems that didn't have good entropy sources. The solution: use operating system entropy, hardware RNGs, ensure entropy is sufficient. Signature vulnerabilities. Some ECDSA implementations had bugs where they reused nonces. If you sign twice with the same nonce, an attacker can compute your private key. This is not a flaw in the algorithm, it's a flaw in implementation. The solution: use well-tested libraries, ensure nonces are unique and random. Entropy failure. If the entropy pool fails or is depleted, your systems can't generate good randomness. This causes slow key generation, or worse, weak keys. The solution: monitor entropy levels, use HSMs, design systems to handle entropy correctly. The lesson is this: cryptographic primitives are strong, but only when implemented and used correctly. A one-character error in code, a weak entropy source, a wrong parameter, these can break security completely. Let's summarize Module 1.2. We covered 4 cryptographic primitives that form the foundation of PKI. Hash functions. These create unique fingerprints of data. They're one way, you can't reverse them. The avalanche effect means tiny input changes cause massive output changes. SHA-2 is the standard. They're used for efficiency and integrity verification throughout PKI. Digital signatures. These prove who created something and that it hasn't been modified. You hash a message, encrypt the hash with your private key, and the recipient decrypts and verifies with your public key. Non-repudiation means you can't deny you signed something. Key pairs, public and private keys, are mathematically related but cannot be derived from each other. Public keys enable encryption and signature verification. Private keys enable decryption and signature creation. Algorithms vary. RSA requires large keys. ECC is more efficient. Entropy and randomness. Keys must be unpredictable. Entropy sources provide true randomness. PRNGs provide fast randomness. Weak entropy breaks everything. High-quality entropy is essential. These primitives never exist in isolation. They combine to create PKI's trust model. Understand these, and you understand the mathematics of security. In the next module, we'll look at what happens when these primitives are implemented poorly or when they're misused. We'll look at real-world failures and the lessons we learned from them.